I'm surprised that there's so many people still here. Shouldn't you all be out drinking or something? Oh, you got it all here. Okay. Perfect. All right.
All right, everyone. Let me introduce Matt, who's going to be speaking about Serial Box.
So I'm Matthew Jakubowsk. This talk is just a 101 intro for dealing with Serial and JTAG. I figure that with the new computers you see out today, they don't really have serial ports on them anymore, but it's still an important interface that you use a lot for debugging on embedded hardware. So if you're looking to get into that, it's important to know the basics. It's still used for testing and debugging, and if you can understand how to use it, you can make the hardware do what you want instead of what it's just programmed to do. So I first got into this several years ago playing around with older hardware. Like that there's a little set-top TV box design that was designed to connect to the internet, and I thought, well, I want to put Linux on this thing. So up there in the upper right corner of that picture is a 4-pin Molex like you'd see on a old floppy drive, and that was actually the serial port. So with that and putting different code on the compact flash card that it used to boot, I was able to get Linux up and running, but as it turned out, it wasn't fast enough to be a Myth TV front end, which is what I'd hoped for it to be, so ended up scrapping that. Later on, I had a little Wi-Fi hotspot called an iSpot that I wanted to play around with, and we were able to find the serial port on it and found that it had an open root shell. And as I'll show you later in the demo, they're not the only ones that do that. But first, serial versus parallel. So on old machines, you'll see both types of ports, but there's differences between the two. And at parallel, it'll use multiple wires to send the bits at the same time, versus the serial will send it one at a time. At the lower speeds that the older hardware is capable of, you've got better throughput that way with the parallel, but with you're able to have a lot higher clock speeds with serial, which is why you see it nowadays even for things like your hard drives and connections to periphery ports. It's like the old IDE connector, that was a parallel interface, but there was a limit to what you could send data with there. Like I was saying, you don't see this on many machines anymore. And while the medium has changed, it's still important to understand how we got from there to what we use in the embedded hardware. You got the basic pin out for that type of port. The only pins you really need to worry about, the transmit, receive, and ground, those are the pins that are actually sending the data you care about. The other pins are for flow control, which can be used in some cases, but for just a basic console, you don't really need them. And for modem signaling, which who uses a modem anymore? It's not always DB9 like you see here. It can come in many different form factors. You got to the right a DB25, which you see on old hardware modems, and really only uses the same 9 pins, even though it's got the 25-pin connector. You got a DIN connector there. It was used for some audio-visual equipment. The RJ45 console port that's still used all the time for switches and routers. And then down there is a 10-pin to DB9 connector. Some motherboards, mainly on servers, still have the serial, but it's not. They don't have the exposed port. But with the 10-pin connector, you can still get access to it. So once you have your physical connection, how do you send data over it? You've got what they call the start and stop bit, which is what lets each side know where the byte begins and ends. You can have eight data bits is usually the most common, but sometimes you'll see 7 bits, which is for straight ASCII on older like teletype machines. Parity is optional. Most things don't use it anymore. And then you have the baud rate, which is the speed that you're sending the data across. Because for this type of serial, there's no clock to let you know when each bit is coming. So you have to agree ahead of time how fast the data is going to come across.
Question.
Yes?
So 8 in 1
yes.
means 8 data bits, no parity, 1 stop bit.
That's right.
Cool. Check.
Now, embedded devices. This one's very nicely labeled. It's got the TXRX and ground right there. Not all of them are that easy, though. Sometimes you gotta play around, guess, get out a multimeter, see, oh, is this 5 volts here? Maybe that's it. Okay, this is the same as a known ground, so here's our ground here. A little bit of trial and error. But once you've determined what your probable serial is, you can't just hook a standard serial port to it because there's different signaling and voltage levels. Because normal RS-232 is usually 12 to 15 volts, and it swings positive to negative, where positive voltage is interpreted as a 0, and then negative voltage is interpreted as a 1. So it's sort of like an AC signal almost. Embedded devices use what they call TTL signaling, the transistor logic, where 0 volts is 0, and the normal voltage of the device, 1.2 volts to 5 volts, depending on the device. 3.3 is pretty common, though, is interpreted as the 1. They've got converter chips to change between these. One picture is Maxim 232. Back in the day, when I was playing around with that old MSN TV, I actually ordered up a sample chip from Maxim to build my own converter, because back in 2004, you couldn't just go to SparkFun and order one of these. But it's 2015, and yeah, I only asked for 2. Took them like 8 weeks to send it to me. But it's 2015, and we all use USB now. And you can get serial adapters everywhere. This one pictured is $15. Nice and easy. And it'll do the direct transistor logic, so you don't have to worry about any extra converters on top of it. Though if you do go through a USB to RS-232 adapter, one thing I've found is it doesn't do the full 12-volt voltage swing. It'll only do to plus 5 volts and to negative 5 volts, which doesn't really matter most of the time, but I saw a video once of someone using an old 1960s modem that the tones didn't come out right because the voltage was different. Is expecting the full 12-volt swing. Next thing that we'll get into is JTAG, which was created in the 80s because it was getting to the point that you couldn't just probe all the points on a chip to test them manually anymore. And in some cases, they were getting into the surface mount chips that you couldn't even easily get to all the points. So this was a protocol designed to be able to do boundary scan testing, which is basically to test all the outputs on each chip. Hardware level debugging, where you can basically get a GDB type setup directly into the CPU of the device you're interfacing with. And then you can also program flash memory, and even access the RAM on the device to write directly to RAM and have the CPU execute that. So to the right, you get the full 20-pin interface that is considered like the ARM JTAG, but the only 5 pins you really need are the input and output pins, test mode select, which lets you select which chip you're actually communicating with, because you can daisy chain multiple chips together with JTAG, so that you can just have one set of test points for everything on the board. And then test clock is to determine the speed, because unlike the RS-232, this is synchronous data. So the clock determines what speed the bits are sent input and output, and then of course the ground. Then on the device, the pinouts are rarely standard, because they're designed for debugging, not for end user convenience. Sometimes they're all up there, sometimes they can be all over. And in some cases you might even have to find one of the chips where it's got JTAG on it and try and solder directly to the surface mount. Yeah. Hopefully you're very good at soldering, because I know I can't solder that well. So for finding the JTAG, Google helps. Failing that, can find data sheets for some of the chips on the board to see where what pins are assigned to JTAG for those chips. If you see some test points on the board but you don't know what they are, a new tool that I've been playing around with, JTAGulator by Joe Grand. It's a little expensive, $160, but it'll let you just hook all the possible test points up and it'll brute force it until it finds the likely JTAG ports. So to interface with JTAG, if you still have a machine with one of those parallel ports like we were talking about, you can do it by hand. You don't want to, though. It's slow. This guy there, he knows. I did it that way once with an old cable modem to put a hacked firmware on it, and Surfboard 51, yeah, something like that. Yeah. But nowadays there's some open source hardware designs that are easy to use to interface with JTAG. A couple I've played around with, GoodFet. I need to play around with that one a little more. That's the setup for it's a little different. BusPart and BusBlaster, though, are easy to configure with OpenOCD, which is open source software designed specifically to work with JTAG. And it'll let you actually run GDB to. Oh wow, really? I'm going fast. Okay. So OpenOCD. I don't have all the screenshots for it, but basically you set your interface config. For example, for the bus blaster, it uses a standard FTDI chip that they've got a configuration for. Then for the device, there's a lot of standard configs in there. Like, say, if you we're doing something to an old Linksys WRT54G, they've got configurations for that to actually do all the flashing stuff for that. If not, you can just give it a basic config from one of the examples in there. And then, if for say to dump the flash, there's the three main commands in there. There's the flash command that lets you see the flash chips that it detects on the board, the dump image to read the flash, and then write image to write that flash. We've been going pretty quick here. Let's get going with the demo. Can you, come on. Okay. So, having screen connect to my USB serial adapter using the FTDI friend that I had the picture up of earlier, and connecting to this device at 115.200. I have, let me plug that though. Okay. It's connected. Now let me apply power to the device. Bam. This is a Sprint Overdrive, which is a little Wi-Fi hotspot device that has cellular functionality. It's booting up. Hi there. Oh, doesn't have who am I? Yeah, it is running BusyBox. What do we have there? Oh wow, that is not easy to read. I was going to do a JTAG demo, but the board I had picked out for that, which was a different hotspot, apparently it is faulty on me, because when I had everything hooked up, it got hot enough to melt the hot glue that was protecting the pins. So much for that one. Okay. And it's easier to get into this than ever, because all the hardware I've been messing around with, you got basic serial $10, or the little more advanced one that's got a couple extra pins and options on it, $15. If you want to mess around with some different bus types like I2C, you can get a bus pirate for $30. The bus blaster I was talking about for getting into JTAG, $35. The most expensive thing is the JTAGulators when you're trying to find the different pins. It's $160. So start messing around with this stuff is easy, and the serial is dead simple, and the JTAG isn't too much harder. Does anybody else have questions? Yes. Yes.
This is use the mic, please. Okay.
So this is going to be a dumb question.
Okay.
I think I heard you say that you can do the JTAG serial connect to. Did I hear right? GDB.
The OpenOCD allows you to use GDB to debug JTAG interfaces, yes.
So this does not compute. I use GDB. I run an executable. I set breakpoints. I stop at some line of code.
Mm-hmm.
So I'm talking to an executable program, and now there's some serial interface where maybe the program is opening a serial port, but how do those two things connect together?
So the JTAG lets you manually change what the CPU itself is doing on like an ARM chip. So it's the CPU level that debugging is going on.
Or you could talk and I would repeat, or you say and I'll repeat it. So you send a signal to the CPU to stall the processor. Then on the JTAG bus, you can read and write arbitrary memory values, including what the CPU is about to execute next. You can ask it to dump things or change code on the fly.
Yeah.
And tell the CPU, now execute it again. Thanks.
Yeah, that all sounds about right, along with being able to read individual values of the pins that are on the chip.
I might ask you to repeat that offline because I can't think and talk at the same time.
Yes.
So I see you got struck with the cursed live demo bug, so I'm sorry about that.
Huh.
But could you explain to us what you were going to show us?
Well, the plan was to show you the connecting to the device with OpenOCD and dumping the flash from that device.
Okay. Thanks.
Any more questions? Okay, let's thank our speakers.
Thanks everyone for sticking around. Time to go party.